Okay, our next presentation is looking at the actual residuals within a tank and activities that were done to characterize those residuals in order to predict releases from them. And our next speaker is Kirk Cantrell from Pacific Northwest National Laboratories.
Thanks. Well, on here I've put some contact information in case in the future you want to talk to either me or my co-investigator, co-principal investigator, Ken Krupka. One thing I want to point out is we make kind of a distinction between sludge and the residual waste that's left in the tank after tank retrieval, because there's typically pretty significant changes in the composition of the material as a result of that process. What I'm going to talk about is the objective of our residual tank waste contaminant release project, the technical approach that we take for testing and characterizing the residuals, some of the solid phase characterization results that we've come up with, and go over some contaminant release processes, including some scenarios and a couple of examples. And then at the end there's a page with some publications, including a web address where you can access our reports and stuff, so that'll be in the materials. We're developing release models of contaminants of concern for residual tank waste to support performance assessments being conducted by Washington River Protection Solutions for closure of the single shell tanks at Hanford. Model development requires testing and characterization of actual residual waste. We determine leach properties, bulk composition, contaminant inventory. We identify the mineral phases that are present and host solids that the contaminants are contained within, and identify solubility controls. We use a tiered characterization approach. This allows us more flexibility because all the residual wastes are quite different in character. For our Tier 1 sludge characterization, we do total elemental analyses, which can include fusion dissolution or acid digestions, and we get basically total concentrations of all the components except for anions, because we're adding strong acids to these tests. For inorganic solution analyses for the leach tests that we do, we measure essentially everything: pH, alkalinity, anions, major cations, trace metals, and radionuclides. And we use this for geochemical modeling to determine solubility controlling phases and adsorption reactions. We also always do XRD analysis to identify any crystalline mineral phases that may be present in the phases. The leaching tests that we do two different approaches. We use single contact batch tests for different time periods. And then we also do sequential contact batch tests where we replenish the solution with a fresh solution 5 or 6 times. Some of the leaching tests that we do are conducted to simulate the impact of a cementitious grout. Grout is being considered as a tank filler to maintain or minimize infiltration and maintain the integrity of the tank. Cements are complex, have complex pore fluids which evolve over time. So to deal with this, we kind of use a simplified approach where we just look at the fresh cement and the aged cement. The fresh cement will initially have a relatively high salt content and high pH, which is essentially controlled by calcium hydroxide. The aged cement has been carbonated, reacted with CO2 or carbonate, and the pH in this instance is essentially buffered by calcite. So what we do for our leach tests is we take these two end members and we simulate the fresh cement with a 0.01 molar calcium hydroxide solution with a pH of about 12. And the aged cement pore water is simulated with a calcite saturated solution, which has a pH of about 8.2, which is also very similar to Hanford groundwater. For Tier 2 characterization methods, these are just a list of some of the things that we do. We don't always do it. It depends on the sample we have. But typically we do SEM, EDS to determine elemental composition of individual particles. And this also gives us morphology data. Sometimes we'll do selective extractions. This is useful for quantifying phase associations between the more mobile contaminants of concern, such as technetium, uranium, iodide, and chromium. Sometimes we'll use synchrotron X-ray techniques. This is useful for determining oxidation state, coordination, nearest neighbors of the contaminants at a microscale. And Mossbauer can be used to identify iron phases. One of the main things that we've discovered is that at Hanford anyway, residual tank waste is very complex and highly variable. Initially, the initial acidic high level waste was over neutralized with sodium hydroxide to a high pH to minimize tank corrosion. And then subsequently, some of these waste self-boiled and ended up self-concentrating. In other cases, like the bismuth phosphate waste, were subjected to uranium recovery processes. The redox and Purex waste were reprocessed to remove cesium-137 and strontium-90. And residual waste compositions in general are highly impacted by the waste retrieval process itself. So with all these complications, the average composition of the residual tank waste is difficult, if not impossible, to predict. So it's really necessary for us to characterize the actual residual waste. This is just to give you a visual feel for the variability of the residual waste in the samples that we're getting. You can see in the C103, it's kind of a dirty, it's kind of a dirty brown color, whereas with C203, we have kind of a dirty brown color with particles that are kind of yellow or orange. These are uranium oxide type particles. S112 is kind of a dirty white color. So that just gives you a visual feel for the differences. This is just a table showing the major phase or compositional features of the residual waste for the 5 samples that we've studied to date. I'm showing the major phases and some important minor phases that we've identified. For tank C103, gibbsite is the dominant phase, and some important minor phases are hematite and some other iron oxides, as well as some uranium oxides. We think it's schopite in this case. C106, gibbsite, bolmite, rhodochrosite, limburgite, and whewellite are important phases. These oxalate phases are the result of the oxalic acid retrieval process. They weren't there initially. important minor phases are dawsonite and hematite. C202 and 203 are pretty similar. The main phase of interest in these two tank wastes were poorly crystalline uranium sodium oxide phase, and there was a little bit of phosphate and carbon in some of these, and it's likely that there was more than one phase for uranium. Iron oxides were an important minor phase for these two wastes. S112 was dominated by gibbsite, and it looked like there was, in some cases, some coatings of dawsonite on these particles. This is some SEM micrographs in backscatter emission mode. We like to use backscatter because it gives good contrast between the heavy elements and the light elements. And the point of this slide is to show you that residual wastes are complex assemblages of solid phases. This is the lower magnification image, and we have some three higher magnification images. Here you can see some aluminum hydroxide, probably gibbsite, and a little nodule here of silver with mercury in it. In this case, we have a particle that's mostly aluminum hydroxide. It also has some calcium, sodium, uranium oxide phase interspersed within it. In this case, you can see we have aluminum hydroxide again, but there's also some iron oxide included within that particle, as well as some uranium oxide. The initial conceptualization of the residual waste that we had was just individual particles of separate mineral phases. We've modified that since because of the complex assemblage nature of these particles. The contaminants may be present in more than one phase. Some of the contaminants have co-precipitated at trace concentrations in minerals that are not present as discrete oxide minerals. Release of the co-precipitated contaminants is going to be dependent upon the dissolution rate of that particular host phase. In addition to these complexities, there's mineral coatings that armor some of these phases, and so that's going to have an important impact on the release of contaminants in contact with infiltration water. In addition, additional filler materials are going to affect the water flow path as well as the pore water waste chemistry reactions that will occur during later contaminant release. Some of the important contaminant release processes that are going to occur, the primary ones are going to be dissolution precipitation. There also may be some co-precipitation adsorption and adsorption desorption. Secondary reactions include complexation, hydrolysis, as well as redox reactions. Testing of the 5 waste samples that we've done so far indicate that dissolution is the dominant control of contaminant release for these 5 samples. Retrieval processes remove readily soluble materials, so what we have left in the residuals are primarily the less soluble, more recalcitrant type phases. As part of our release model data that we provide, we've come up with 2 different release scenarios. In the first scenario, we assume that the tank is filled with a relatively inert material such as gravel or sand. In this case, the infiltration water is assumed to be in equilibrium with calcite, essentially the same as Hanford groundwater or Vadosone water. In the second scenario, that's where the tank is filled with cementitious grout. For this scenario, there's going to be two stages. The fresh cement stage, where we have a high pH in the pore water, and it's dominated by calcium hydroxide. And then the stage 2 is where it's been completely carbonated and the pH is buffered by calcite. And something else to point out is that the aged grout scenario for stage 2 is essentially the same as scenario 1. So that kind of simplifies things a little bit. This is just an example of some of the release data that we've have, and I will point out a few interesting features of some of this. If you look at C202, well, let me back up a little bit. I'm showing release data for the 3 primary contaminants of concern, and I'm showing data for both the fresh and the aged cement scenarios, and I'm also showing the sludge concentrations in the solid phase, and then the release concentrations that we've provided for the release models. And you can see in the case of 202, technetium concentrations in the sludge are relatively low, and the release concentrations are also relatively low, and that the concentrations of technetium that are released for both scenarios are very similar. And the reason for this is that the technetium is being bound up. What's left in the residual waste, the technetium that's there, is bound up in iron oxides, and so the release is related to the dissolution of the iron oxides rather than the normal high solubility that you see for technetium. In the case of uranium, for C202, if you notice, this is really high concentrations of uranium. That's like 24% by weight uranium. And you see that the scenario has a tremendous impact on the release concentration that you see. The calcium hydroxide is reacting with the sodium-uranium phase, converting that to a calcium-uranium hydroxide phase, which has a much lower solubility. Whereas in the case of the aged cement, carbonate complexation leads to pretty significant solubility in this case. For chromium, for C202, we have pretty high concentrations of chromium. In the fresh cement scenario, we have significantly larger release concentrations, and we believe this is due to the higher pH is increasing the oxidation rate. And in contrast, for the uranium, if we look down here for C106, you see the uranium concentration is much lower, and the release concentrations are much lower. Plus, there isn't a very significant difference between the fresh cement and the aged cement scenario. So in this case, we believe that the uranium is also locked up in recalcitrant phases such as iron oxides, similar to what we saw up here for technetium in both of these samples. This is just another set of data. This is showing our sequential leach test results in terms of percent leachable for uranium. And one thing I want to point out here is that these stages have different contact times. Most of them are for 1 day, but the third stage is for 3 days, and the last stage was for 30 days. And the results for the DI water leaches and the calcium carbonate water leaches are fairly similar. The reason for this is there's quite a bit of carbonate in the sample itself, which dissolved and made its final concentration similar to that of the calcium carbonate leaching solution. And what you see is fairly high fairly high percentages of the uranium coming out initially, and then with subsequent leaches it goes down, except for in the third leach it goes back up again with the higher contact time, and it goes down again, And then on the final contact, it goes up almost as much as in the initial stage. And this just goes to show the complex dissolution kinetics that we see. That's the main point I wanted to make here. And then again, you can see that the calcium hydroxide is converting the sodium uranium phase to a very insoluble calcium uranium oxide phase. Initially it's way down, but it continues the subsequent stages, it's even lower. And then when you allow 30 days, this conversion process to this other phase is even greater. So the contaminant release models for tank waste that we've developed so far are primarily empirically based. This is mainly because it hasn't been possible to identify the solubility controlling phases for a number of the important contaminants of interest with certainty. The contaminant phase concentrations are typically too low to be detected by solid phase characterization techniques. And some contaminant solubility controlling phases are amorphous. This creates problems because the contaminant concentrations within these phases are often variable, and getting thermodynamic data and kinetic release data for these amorphous phases is problematic. So in summary, the long-term release predictions required for residual waste require adequate characterization of the residual waste and actual measurement of the release parameters. The presence of a large variety of minerals and other solids in the waste may require a combination of mechanistic and empirical release models. Significant fractions of technetium and other typically highly mobile contaminants have been found to occur in recalcitrant phases and are resistant to dissolution. Releases from closed tanks must consider contaminant interactions with tank filler materials and other tank components such as the steel tank and the concrete around the tank. Determining cross-cutting characteristics between the different tank types would allow grouping of residual waste, and this is an important goal for us because it's not really possible to test the complete range of tanks that are out there, the hundreds of tanks. So that's one of the goals that we have. So that's it. Thank you.